Now let's look at some implementations of MapReduce. So the first one we're going to look at is Apache Hadoop, and it's the first open source MapReduce implementation. It's managed by the Apache Foundation, which brought us the Apache web server and many other open source projects. So Apache Hadoop is named for a child's name for his little stuffed elephant. He called that elephant Hadoop, and the lead developer for Apache Hadoop needed a name for his project, and so he took his kid's name for his little stuffed elephant. So that's why the logo is an elephant and the name is Hadoop. So it's based on Google's approaches to MapReduce and the Google file system. And so it implements both of those, a MapReduce compute framework and a distributed resilient storage framework called HDFS. More on that in just a moment. So a bunch of companies have been formed around Hadoop, including Cloudera, Hortonworks, and MapR. So it's a very active open source ecosystem. There are a lot of developers working on Hadoop and the related technologies. As I just mentioned, the distributed file system, it's called the Hadoop Distributed File System. There's also the MapReduce Compute Framework and Yarn. Yarn stands for Yet Another Resource Manager, and it's basically how you manage the machines in a cluster that you want to run MapReduce jobs on. Hive is for SQL queries running on top of MapReduce. So, and there are a bunch of other key technologies that are part of the Hadoop ecosystem. The downside to Hadoop is it's very tedious to use. So first of all, you have to know Java, and the number of programmers who know Java is not as large as it used to be. The other downside is that it's very verbose. So that word count example that we saw, it would take hundreds of lines to implement that for Hadoop, when really the basic functionality that we think we need for the algorithm should be really concise and easy to specify. Unfortunately, that's not the case with Hadoop. So the other thing to think about with Hadoop is how it operates. So the first thing that we do is we read our input data from HDFS, read it from disk across many machines, and then we perform our map operation. When we complete the map operation, we save the data to disk. That's HDFS writes that occur. And then the reducers, they read that same data that we just wrote from HDFS, perform the reduce operation, and write out to disk doing HDFS writes to save the results of the reduce. So each of the stages ends up passing through the hard drives. And if we look at iterative jobs, they have a lot of disk I/O, right? Because we do initial HDFS read, do a map, do an HDFS write, then we do an HDFS read, do a reduce, do an HDFS write, and then we repeat the process for the next map and for the next reduce, and so on. And the challenge here is that disk I/O is very slow. Why? Well, there's a couple of reasons. One is physical. It takes time to read data from a disk. It takes time to write data to a disk. But in addition, we have memory. In memory, we have objects. On disk, we have byte streams. And we have to convert from a byte stream on a disk into an object in memory. And that requires compute. So reading from a disk requires both the I/O of reading the bytes from the disk, but it also requires compute to take that serial byte stream and turn it into an object. When we want to write to the disk, it's the opposite. We have to take our object and turn it into a serial byte stream. And then we actually have to transfer those bytes to the disk. So again, we have compute and we have disk I/O. So the disk I/O that we see here between the stages is actually very, very time consuming. And for some computations, we might actually spend more time on disk I/O than we actually spend in the stages of our iterative computation. If we look at complex jobs, if we look at interactive queries like interactive data mining, if we look at online processing like for streaming, we see lots and lots of disk I/O. So for interactive mining, we have a data set that we want to run queries on. It's the same data that we're running the queries on, yet each of the queries has to read the data from disk, turn it into objects, and then run the query on those objects. Similarly with stream processing, we're reading data in from disk, processing it, and adding new data that we receive that comes in from disk, and then processing it, writing it to disk, and going on to our next stage. So, and then again, iterative jobs, which we've already seen. In all of these cases, the disk I/O we have to do is very slow. So let's step back a moment. If we look at today's clusters and cloud computing, what do we see? We see lots and lots of hard drives. Disks are very cheap. We see lots of CPUs. And those CPUs actually have multiple cores. They might have 4, 6, 8, 12, or more cores. And we see lots and lots of memory. The largest machines in the cloud have nearly 1 terabyte of RAM. So, there's an opportunity here. The opportunity is we can keep more data in memory. And we can do that by creating a new distributed execution engine. And so that's what we did in the AMP lab that I was part of. That's the Algorithms, Machines, and People lab here at Berkeley. We created Apache Spark, an in-memory data flow system. There's a couple of research papers that have come out of it. These are perhaps the most important papers, and I recommend that you take and read them. Okay, so how does this work? So remember when we were just looking at HDFS and MapReduce, we did everything by reading and writing from HDFS. So between every map and every reduce, we had an HDFS operation, either a read or a write. What we're going to do for queries is the same thing. We're going to read from HDFS before each query. Want to do another query? Have to read the same data again from HDFS. So the Spark idea is that instead we're going to read and write from disk only at the very beginning and at the very end. So for our iterative computation, we read initially from HDFS, convert it from on-disk data into objects, and now every iteration runs on that in-memory object. New objects that are created are stored in memory. The next iteration, which is using those new objects, can just reference them directly in memory. And the objects it generates are also stored in memory. Similarly, when we're doing our interactive data mining, we read the data in once, deserialize it from the byte stream, convert it into objects, and now all of our queries, they run on those objects that we have in memory. This can be really fast, so up to 100 times faster than going over the network or going to disk. So, what is Spark? So at a high level, Spark is a parallel execution engine for big data processing. It's very efficient and supports multiple sets of workloads. So for example, the traditional batch workloads we see in Hadoop, and then it also supports interactive workloads and streaming workloads. It's really easy to use. So you have a fraction of the code that you would write for MapReduce, and it has high-level APIs in R, Python, Java, and Scala. Not just Java like MapReduce. And again, much faster, up to 100 times faster than using MapReduce. And it's capable of exploiting memory when it's available. If the objects are really, really large, then you can spill out the disk and it'll treat memory as a cache. And then finally, it has a low overhead scheduling engine and also an optimized processing engine. So what makes Spark tick? So here's the thing. What makes a good programming language and environment is the data structures. And in Spark, it's all about writing programs in terms of transformations on distributed data sets. And so what is that distributed data set? It's an RDD. RDD stands for Resilient Distributed Data Sets. So you can think of it as a collection of objects that's distributed across the machines and can be stored in memory or stored on disk. You build RDDs, these distributed data sets, Through operations, parallel transformations on the data. Transformation takes an RDD and transforms it into a new RDD. And these are things like map and filter. Now, what makes an RDD, the R in RDD, is that it's resilient. So if a machine fails while you're doing a transformation, if a disk fails, if an RDD that's stored in memory is on a machine that fails, none of that matters. The RDD will automatically be rebuilt when you need to use it. So that makes it resilient in the presence of failures. So these RDDs, again, collection of objects that are automatically partitioned and distributed across a set of machines in a cluster or in the cloud, stored in memory or stored on disk, and resilient in the presence of machine failures, network failures, disk failures, memory failures. We work with RDDs with operations. Two types of operations: transformations and actions. So transformations take an RDD and apply a function to that RDD, generating a new RDD. Now, the thing about transformations is that they're lazy. And what that means is that when you specify a transformation, Spark says, okay, I'll make a note that you want to apply this function to an RDD. I'm not actually going to run it. I'm just going to make a note that you want to do this operation. Examples of operations are map, filter, group by, and so on. Actions are the other type of operations. And actions actually trigger computation. So an action could be something like count. So you could have done a map, a filter, a group by, and nothing actually happens. When you do a count, you want to count the number of objects in that RDD. That's when Spark will take and look at all the transformations you want to do. And it'll optimize them. So if it can see, oh, you're doing a map and then you're doing a filter, well, maybe I can avoid doing some of the map operations because I see that there are filters or group bys and so on. And so Spark has a query planner that looks at the set of transformations that you want to perform and optimizes what data actually needs to be read, what data actually needs to be touched and processed, and minimizes the overall I/O and computation. So it's very similar to what we saw in databases, where we have a query planner and optimizer that tries to avoid doing unnecessary I/O and computation. But the one caveat I will say is that lazy computation is something that is very difficult for students and programmers to understand. The reason why is because if you have a bug in a set of lazy operations, they don't actually, that bug doesn't manifest itself until you actually trigger the computation with an action, which could be in a much different piece of code from those transformations. And so you don't see the immediate error that you see with immediate execution. Rather, you see an error that occurs much, much later in your program. So it can be a lot harder to debug programs that use lazy computation. That's the price we pay. We get optimized execution, but debugging and writing our programs can be a little bit more challenging. Okay, so I don't want to go through this table in full detail, but the important takeaways are the execution model is different between MapReduce and Spark. So in MapReduce, you only can do batch execution, so you give a program and it runs. Whereas in Spark, we can do that, but we also can interactively at a command prompt work with our data and run operations. And you can also deal with streaming data where we have data continuously coming in and we want to continuously apply functions to that data. The other big difference is around programming environments. Only Java for MapReduce, and for Spark, we have Scala, Java, R, and Python. And again, the biggest difference is that MapReduce operates off of the disk. Spark can use memory or disk or both. Now, what are the benefits we get? Well, here are two machine learning algorithms that we've already looked at in this class, k-means clustering and logistic regression. We know those are iterative algorithms, right? And what we see here is a graph where on the x-axis we have time in seconds, and we have in blue Spark and in red Hadoop MapReduce. And shorter bar is better. That means it's running faster. And what we see is that Spark is really fast, right? Because most of the time that we're going to spend is just that initial read from disk, and then the compute is actually really short. Whereas with MapReduce, we're constantly reading from disk, writing to disk, reading from disk, writing to disk, and also serializing and deserializing our data from the on-disk format into in-memory objects and vice versa. And so that's why we see such a difference between the MapReduce execution times and the Spark execution times. So Hadoop set a record for being able to sort 102 terabytes on a private cluster at Yahoo in 72 minutes. It took them 2,100 nodes to do that. Spark was able to do that in a public AWS cluster using only 206 nodes in 23 minutes, sorting 100 terabytes. This is the Daytona Gray 100 terabyte sort record winner. It's currently tied for first place. And they were able to actually see, well, how much larger could we sort? They sorted a petabyte, so 1,000 terabytes. And it took 234 minutes on 190 machines. So this really is kind of a democratization of big data. The ability to work with a petabyte of data and do it with only 190 machines. That's not very expensive in terms of the amount of cost for those 190 instances on Amazon for 234 minutes. So not a lot of time either. Okay, so now let's switch gears and look at an example of doing log mining using Apache Spark. So we're going to load error messages from a log into memory, and then we're going to interactively search for various patterns. So we've got our set of machines. Here we have 3 machines that are workers and 1 machine, which is the driver. And you can think of the driver as being the controller. It's the thing that's going to tell the workers what to do. Okay, so our first line is we're going to read a text file from HDFS. So this is going to create lines, which is our base RDD. Now, when we execute that, what happens? Actually, pretty much nothing. All that happens is that the driver records, oh, you want to read from this distributed file. That's it. It doesn't actually read from the distributed file. So you can see it doesn't tell the workers to do anything. It just makes a note. The programmer said they want to read from this text file. Okay. Next thing we do is we do a filter. So we're going to filter out lines that start with error and only save those lines. So we're going to create a transformed RDD that contains those lines that start with error. Again, nothing happens. All we do is record another operation. So we now have a chain of operations. The first operation is read from the HDFS file. The second operation is to do a filter, but nothing has actually started running yet. Okay, next we're going to do a map. Again, another transformation. What we're going to do is we're going to split into by text fields, and we're going to take the second one. And then we're going to cache that result of those messages. All right, so now we're going to do a filter to look at the lines that contain MySQL. And then we're going to count them. So filter, that's a transformation. So all we're going to do is add that to the list of transformations that we want to do. But count is actually an action. And so count is going to kick off the computation. And so what's going to happen? Well, we're going to start by the driver's going to tell all the machines, all right, read from HDFS. So each one of them is going to read into memory. And then it's going to give it the set of tasks to perform the filter operation, then perform the map operation. And so they're going to read from the HDFS partition, then they're going to do the filter, they're going to do the map, and they're going to cache the resulting messages in memory. And then they'll run the filter for MySQL, count, and return the results. All right. Now, if we do another filter, what's going to happen? So we're going to do a filter now looking for PHP lines in our log file and count them. Well, Spark is really smart. It knows that you told it to cache messages, and this is a filter being applied to messages. And so it saves messages, and now when it sends out those tasks to the workers can just process that filter by looking at the data that's in the cache, the saved copy of messages that's in the cache. Then it'll return the results back. So caching your data, much faster results. And so to do a full text search of Wikipedia, 60 gigabytes on 20 machines, we can do that in half a second when we're operating out of memory, versus on those same 20 machines would be 20 seconds if we were operating off of disk. So huge reduction in the amount of time that it takes to do queries. And especially here where we want to do repeated interactive queries, we pay that initial startup cost for the first time we have to read things in and do the filters and maps. But after that, now we're operating on our process data at memory speeds. Okay, so we've looked at what it means throughout this class to do compute locally. And then we looked in this lecture at what it means to do compute in the cloud. But now I want to come back for a moment to computing locally. So if we look at the data science tools that we have to work with data locally, these are tools that are efficient for megabytes of data. And you've worked with these tools throughout this semester. Now, today, we looked at tools that were efficient when we want to operate on hundreds of gigabytes to terabytes to petabytes of data. So we looked at Spark and we looked at Hadoop. But there are other tools out there. And so we have these two sets of tools, one set that's really good if we want to work locally with our data, and one that's efficient if we want to work with data in a cluster or in the cloud. But there's this big gap between them. And if we look at the world today, it's changed a lot from when we developed the tools on the right, even. So now we have machines like desktops and laptops that have many cores and have lots of memory and have lots of data that we can work with. Right? And so when we look at the tools on the left, they follow typical programming styles. They're widely used and understood in production. Most college graduates, they learn how to work with Python. They learn how to work with that set of tools. Scikit-learn, NumPy, and so on. But those tools don't scale well. They were designed for when we had machines that only had a single core. Now you have desktops that have multiple sockets, and you have laptops that have multiple cores, 6 cores, 8 cores, or more. But when we look at the tools like we saw today, debugging can be a lot more complicated. The lazy evaluation, people really don't like that. They don't really understand it. It makes it a lot harder to debug your programs. You also have to understand how the data gets partitioned across dozens or hundreds or thousands of machines. And these are finally tools that were developed by systems people, primarily for systems people to use them. Very different from the tools on the left, where they're oftentimes designed for people who don't know anything about computers or programming to use. So, we've created, in my research group, a tool that bridges the gap. It's called Modin, and it's a drop-in replacement for Pandas. And it allows you to use the same Pandas API that you're used to, but working with data sets that are in the hundreds of gigabytes or larger range. Now, how hard is it to actually start using Modin? It's actually really easy. All you have to do is replace that line of import pandas as PD with import modin.pandas as PD. And to get Modin on your machine, all you have to do is pip install Modin. So you can accelerate your pandas workload by just changing one line of code. Now what will you get? Well, you'll get the ability to work with larger data sets based on the amount of memory that you have on your machine. And if you have a multi-core or multi-socket machine, you'll also see significant speedups. So you can work with data frames that are a megabyte in size or a terabyte or more in size. And you'll see speedups that are relative to the number of cores that you have available. So on a 4-core laptop, you'll see up to 4x speedup in performance. So basing it on the Pandas API was really a good idea because as a drop-in replacement, it makes it really easy for people to switch to using Modin. We have over 5,300 GitHub stars, and there are over 41,000 installs every month with over 400,000 downloads and installs since the start of the project last year, in July 2018. We've reached overall trending on GitHub multiple times. That means we're the top starred repo of the day, and our user base comes from small to companies all the way through some of the largest companies, government labs, and government agencies. What makes Modin possible, and I'm not going to go through this architecture picture in any detail, is that it has a query compiler that lets us optimize the operations that Modin is doing, and then it has execution environments like Ray, Dask, and others that allow us to distribute the computation across the compute resources that you have available. Okay, so summarizing this lecture, we looked at the extract, transform, and load process. It's the way that we take data from operational data stores into a data warehouse and create a historical record of our data. There are many different ways we can organize a data warehouse, all sorts of different schema organizations like Star and Snowflake and so on. Online analytics processing is a technique that allows us to analyze the data that we put into our data warehouse. So it lets us work with this historical data at scale. Now, modern days, we're adding in unstructured data, and that's very hard to store in the tabular format that we typically find in a data warehouse. And so that's led to a new paradigm of the data lake, where we store the data in its original format and then apply the schema when we actually want to read the data and access it. Data lakes are enabled by two key technologies, distributed file systems and distributed computation. And distributed file storage includes the replication and partitioning of the data. We'll get better speed and reliability, but we pay a cost by doing replication. But it allows us to use less expensive hardware. So we can use commodity hardware, which is going to fail at a higher rate and basically deal with those failures in software. Distributed computation is made easier by paradigms like MapReduce. Apache Hadoop is an open source implementation of Google's MapReduce and the Google file system. Apache Spark is almost always faster and is a lot easier to use than Hadoop. You can program in Python. And finally, Modin is a drop-in replacement for Pandas that accelerates local data exploration.